Hello everyone. In this part we will talk about digital modulation, the PSK. So phase shift keying. So as you know that we learn about the ASK, OOK, FSK, and this is now PSK. So in FSK we did the modulation with the frequencies, but in PSK we the phase will be changed according to our input bits. So here is the input pattern data stream. So 1 0 1 0 1 1 0 1 0. Okay, so as you see that data stream, when we are getting high or we are getting 1 at the digital data, so the frequency will start from here. So it's a like positive, the sine wave started from positive end, and when we are getting 0, the phase is actually shifted here, so it start with a negative end. So this is actually the technique of PSK, very simple one. So again, when the data changes, the positive will be there, and when 0 is there, so 0 is, yeah, negative. It will, the sine wave will start from negative end. So this is actually the technique of PSK. So how it works. Now we will consider that how we can design a PSK modulation, and also how we can demodulate the PSK modulation. So if we talk about the mathematical term, so if we say that if our message signal is this one, and if we have like if we modulate this one, we will get the PSK form of theta. So whenever we are getting 1, then our this this will not have any phase shift. Okay, so we will get like something like this. Plus 0, but whenever there is this is for input 1, this is for if the input is 1, and we will have a phase shift when the input is 0. So which will be actually minus of a cos t, and here we will get actually a cos ct. So this is for input 0, and this is for input 1. So previously in FSK we designed the modulation by using two kind of carrier. Here also we need actually two carrier, but now one will be as a phase shifted one. So for this one, if we are sending the message signal, so one will go with this, so we have message signal, we need a carrier of this thing, so it can be a sine wave. But this message signal, we need to actually uh, get the negative version of this message signal. We can add the same carrier over here, sine wave, the same carrier, but for message signal we actually need to know the negative message signal. The carrier will be same, in the same frequency, everything will be same. So to do that, we have to actually make the negative version of this one. So how we can do, if we minus subtract this one constant 1 from this signal, we will get actually the negative version of the data, and then we have to put it in this sine wave, actually the product. So this is actually product, so we are modulating from here, so P, and after that actually we have to add the signals. Now this will be actually our modulated signal. So after getting the modulated signal, if we transmit it again, we will have some noises. So if we put the AWGN, that wide Gaussian noise system, so in the system it will add some noises, and from that actually again we need to demodulate that signal. We need to demodulate that signal. So to do that, again from the signal actually we need a detector. So detector is actually like a modulator, so it's a product. We need to multiply this signal with the same carrier. So this is also a sine wave. After that, what we need to do, we need a low pass filter. Again we have to design a low pass filter. So after that, again the same as FSK, we need to compare with 0. If it is greater than 0, we will get the 1, and if it is less than 0, we will get 0. So this is actually our demodulated data. So this is very simple. If you understand the FSK simulation part, it will become more easy because it has less work to do. So here actually we are getting two separate signal. So for this one, all the signal will be depending on our input bit. If our input bit is 1 0 0 1 0 0 1, if we make it like this, so as it is 1 for the first, so it will start a positive end, and then as we are multiplying with the data, so next one is 0, so we are getting 0 over here, then next one is 0, again 0 over here, then 1, so we are getting another frequency over here, and again we are getting 0 0 and then 1. So in both carrier the frequency will be same, and in this point actually we will get the invert of this thing. So in these cases we will get the 1. So the graph will be like So if it is it will become 0, and it will become 1, it will become 1, it will become 1, negative version. So the in the first case we are getting 0, but in from here we will get the phase shifted 1 for 2 cycle, and then again we'll get 0, again we are getting 1, again 0. And if we add these two things, so what we will get at this point, we'll get something like this. So this will be high. Okay, then the next start will be from here. Okay, so then again 1, so it will start from so actually it will look something like this data. This will be the pattern. So that's all from this part actually, and in the next part actually we will design the modulation and demodulation part in the Simulink. Thank you. Hello everyone. So in this part we will talk about the modulation and demodulation of PSK. And before starting this video, please watch the FSK video first, then it will be more easier to understand. The whole Simulink block diagram is similar to FSK, but there is little bit change. So as you remember from the theory part of PSK that we need data stream. So this is the Bernoulli binary generator. From here we will get the input data stream, and this is the setup of this thing. Is similar to FSK. And now this will go to our modulator, and with the carrier wave. So we use here sine wave, and here is the this is also the time base, and the sample time is 1 by 5000, and the frequency is 1 kilohertz. And for the another part, the inverted phase part, we have to get the negative value of the data. For that we subtract 1 from all the bit, then we will get the negative version of the data stream, and this is modulated with the same carrier wave. So this is the specification, the same. You see the 1000 hertz, and the sample time is similar. Now these after modulated these two separately, we need to add them together. So we use this sum block. So after adding that, actually we will get the modulated signal. So when we will do the simulation, we will see how the things will look like after each of the step. As you see, we use the scope over here and another scope here, and we also, if you want to see the FFT of the signal, then spectrum of that signal, you can also use the spectrum analyzer. And then we added some noises in the modulated signal data, and then if you want to demodulate that one, we need to first modulate again the sound wave, the same carrier, with the received signal. So here we did the product again, and after that we need to design the filter. The filter design is same as the previous one. If you see the FSK part, so it's similar to that. So we use the same p pass, but you can always changes the value to make it more efficient. So you can play with this data to make the system more efficient. Actually the LPK like low pass filter will be more uh, efficient. So after that we compare the data with respect to 0, and then we will get the modulated data. So this is the whole block diagram of the PSK system. Now if you simulate this one by placing the run button, we'll see the output. So it will take some time. If you use more spectrum analyzer, it will take much more time. And if you don't want to see the spectrum, it's okay, you can always comment out this one. So this is the simulation, and so if you want to see all the data, so here are our data. So first of all, this is the transmitted data. The Bernoulli binary generator generate this data. So it start with 1, then 0, 1, 0, 1, 0, 1, 1, then 0, 0. Okay. So if you see the carrier, this is actually product of that total carrier, and this is the carrier spectrum. You can see the it is 1 kilohertz all, and if you zoom it, so in the beginning you see that this is it started with the positive end because the first one is positive. Okay, now the second one is actually 0. So let's check this one. If you zoom, so after 1, the next signal is started from a negative phase. So this is 180 phase shifted. So you can see that for 1 we are getting the positive, and for 0 we are actually getting the negative part, negative phase, and this is similar for all the cases. So if we go again here, it goes from 0 to 1. So this is 0, this is starting at 0.6, so around here. So from 0.6 is actually going to 1, from 0 to 1. So you see the phase is shifted to 1. So after adding these two signals, we will get the modulated signal. So as the frequency is very high, you can zoom it here. So this is 0.1, and this is actually 0.1. If you zoom this one, this is 0.1, and let's go to 0.1 of this system. This is 0.1. So in the 0.1, actually the data goes from 1 to 0. You can see that when they are separated, not added together, it's from 1, it's going to 0, and here these two signals are added. So when the data is changed at 0.1 timestamp, the phase is shifted. So after that, if we add the noise, you will get something like this, and this is very hard to read it with empty eyes. That's why we need some modulator to modulate this data, and after multiplying that carrier wave again with this signal, we'll get something like this. So you can see the first one is 1, then we are getting 0. So here we have lots of noises and some others band. So this is high, this is low, and then high again, low. So something like that. This point is this point. So you can understand by seeing with our bare eyes. So if we design the LPF like low pass filter, then but after implementing the low pass filter, we'll get something like this. So this is noise free data, and only the high frequency, low frequency is passed here, and other noise are reduced. So if you get this data is almost done, now you have to compare this data with respect to 0. That means if the signal is greater than 0, we will get high, and if the signal is less than 0, you will get low. And that's is done in the next part, the demodulated data. So when we compare this signal with respect to 0, then we will get 1. So this delay is because of design of our LPF. So you can play the value of L stop and L pass to decrease the delay. So here you see we are getting 1 here. So this is the first data, then 0, and if we, so we are getting the same. This is the transmitted data and this is the demodulated data. So 1 0 1 1 1 0 1 1, the data stream is same as we transmitted. And if you see the all the spectrum, so this is the carrier spectrum, the 1 kilohertz carrier spectrum, and when these two are added, the frequencies, the value of the RMS is getting less over here, and after adding the noise, you can see there is lots of spikes at other frequencies also. But our main target is to detect this one, and that's why we modulated this signal to increase the value. So this is the modulated one, and after applying the low pass filter, we are getting this kind of value. So it's still, this is not smooth, but when you are comparing this thing, you will get very smooth data, modulated data. So this is our demodulated data. So that's all from the PSK part. So if you have any question, you can always ask at the live session. So thank you all.